Hello, nice to see you. Hi. Good afternoon.
Hello.
Yeah, let's maybe wait one more minute so other people will have a chance to join.
Good afternoon.
Hello, nice to see you guys. Okay, so last time we discussed and derived equations for periodic motion of pendulum. We considered regular simple pendulum, also physical pendulum, and derived equations for their motion, and also discussed how pendulum can be used to determine, for instance, acceleration of free fall or unknown moment of inertia of the physical pendulum, some arbitrary shape, a rigid body, with respect to any point about which the body will have an option to rotate if the center of mass of this body is known. So we can easily measure distance from the center of mass to this point about which the pendulum, physical pendulum, can rotate about, and substitute in the simple derived equations which we got during last discussion. So that was in the scope of our previous discussion of simple harmonic motion, and like all of these guys, these examples, they represent some simple harmonic oscillators under ideal conditions. So I mean, for instance, spring block system, simple pendulum, physical pendulum, all these examples represent simple harmonic oscillators, and we consider them under ideal conditions when we don't have any friction, any damping of this oscillation. So mechanical energy does not dissipate, and we always have this conversion between full conversion between kinetic and potential energy of this periodic motion. However, in real life, we like all these systems experience at different extent some damping because of friction, also because of some drag force. Even if pendulum is moving in air, there is some small but measurable drag force which affects this periodic motion. And over time, obviously, it will decay. So our goal for today is to focus on such type of periodic motion when we have oscillation with damping. We will consider two cases, some overdamped and underdamped periodic motion, we'll focus most our attention on this underdamped periodic motion because that is the most interesting one. If it's overdamped, it will be just exponential decay without really periodic motion, just decaying because friction or drag force will be so strong that it will not allow any oscillation to occur. And that's why it's called overdamped. So let us switch to the slides, and we can start with the quantitative analysis of these particular cases. Interesting somehow. 1 second. Okay, now it works. So, as you may remember from our previous discussions, we were considering some relationship between the, when dealing with the spring block system, relationship between the spring force and acceleration, like mass of the block times acceleration. So previously we had minus k times x, that was equal to ma. However, if we have damping, we need to take this into account, and we can write here minus b times v. So we assume that we have some drag force, and this drag force is proportional, linearly proportional to velocity. It's one of the cases we considered earlier when we mentioned about drag force, and that happens when we have not very high velocities. So we consider this case, and we then can write the differential equation based on this equation, this relationship. So we know that acceleration is second derivative of position x. So we can write m times d square x over dt square. Then it will be plus, we can write, here we have velocity, which is first derivative of x over time. It will be plus b times dx over dt. And on top of that, we have also contribution from the spring force, and that is k times x equals 0. So this is a bit more complicated differential equation. As you remember, previously we didn't have this term. So we had second derivative and function itself, x. However, here we have additional first derivative as additional term. So this is also second order linear differential equation. However, it's kind of in full format with second and first derivative. So since it is the same type of equation, differential equation, we also need to write down this characteristic equation and solve it. So characteristic equation, let us maybe get rid of this m next to a second derivative. So if we divide it by mass, so we can rewrite like this. It will be b over m and k over m. Okay, so now we can write a characteristic equation. Lambda square plus, now we have first derivative, so it will be lambda. So we write b over m times lambda. And here is just k over m. K over m. This is equal to 0. So now let us get the discriminant of this quadratic equation, quadratic characteristic equation. So discriminant will be b squared minus 4ac, and according to our particular case, it will be b over m square minus 4 times k divided by m. So this is our discriminant, and the solution of this quadratic characteristic equation. We have two solutions, lambda 1 and lambda 2. That will be minus, let's write general. So it will be minus b plus minus square root of discriminant divided by 2a. So we have minus b over m. Then we have plus minus square root of our discriminant, which is this guy, will be b over m square minus 4k divided by m. And here we will have just 2. So if we rearrange this denominator with 2, so we can write minus b divided by 2m plus minus square root of b divided by 2m square minus k divided by m. Okay, so now we have the solutions of our characteristic equation. And before we proceed further, for convenience, in order to reduce number of terms we use, we should make the following substitutions. So let us denote gamma as b divided by 2m, and omega 0, let us denote it as k divided by m. As you remember from previous discussions, when we considered ideal spring block system, k divided by m was our angular frequency. So here we use omega 0 as intrinsic angular frequency of this system, which does not take into account any effect of the drag force. And drag force is taken into account into already into this parameter gamma. So now we can rewrite our solutions for lambda 1 and 2, taking into account these substitutions. So that will be equal to minus gamma plus minus square root of gamma square minus omega 0 square. Okay, so this we remember, and we will write it on the next slide, because we will work with these solutions afterwards. So it minus gamma plus minus square root gamma square minus omega naught square. Okay.
Excuse me, Professor, then shouldn't have we written that omega 0 equals to a square root of k divided by m?
Square root of k divided by m. Why, wait a second.
Because you wrote that k divided by m is the square of omega 0, or and it doesn't align with the previous one.
Need to double check. So if we have, so that was square root, we have Yes, yes. So here we can write, we need to write like this, or we write that omega is equal to square root of k divided by m, or omega not square is equal to k divided by m. You are right, because here we have omega not square. And yes, because omega was equal to square root k divided by m for ideal case when we didn't have any damping. Okay, thank you for your comment. So now everything should be correct. Okay, let us write this down again or on the next slide and proceed further. So our solution now will be final form 1 lambda 1 2 is equal to minus gamma plus minus square root of gamma square minus omega naught square. And now further, like the form of the solution of our differential equation will depend on the form of this like actual solution of this characteristic equation. So if, for instance, we consider or so-called overdamped case, for overdamped case, we have gamma larger than omega naught. So this is a condition, means gamma is coefficient proportional to the effect of damping. So if damping is very high, then gamma is larger than intrinsic, let's call it intrinsic angular frequency omega naught. So in this case, our characteristic equation will possess two real solutions because gamma is larger than omega naught, so the expression under the square root will be positive, and that's why we have two real solutions. Now, how we can express this? So it will be in the following form, according to the rules for solving this second order linear differential equations. So our position as a function of time will be given as constant C1 times exponent lambda 1, it's like first solution of our characteristic equation, times t plus C2 times exponent lambda 2 times t. So that is the general form for solution. And we can write, instead of lambda 1 and lambda 2, corresponding equations. So let us do it to have in the full form this solution of our differential equation. It will be C1 times exponent. Here, lambda 1 is minus gamma plus square root of gamma square minus omega naught square. And this times t. Then we have another component. It's plus C2 exponent minus gamma. And now we subtract. It's minus square root of gamma square minus omega naught square. And that is multiplied by t. So now we have this. We can take out of the parentheses exponent minus gamma times t, because we have both the same in both terms. So we can write that it will be c exponent minus gamma times t. Then in the parentheses, we will have c1 exponent square root of gamma square minus omega naught square times t plus c2 exponent here minus square root gamma square minus omega naught square times t, and close our square bracket. So this will be the form for solution. Of course, we will have two constants. We will not go into details defining these constants for some specific case, because then we need to consider that x at 0 is some x naught initial position, then dx over dt at 0 time should be equal to some v naught, some initial value of velocity. So it can be any position and velocity. Depends on that, we will get some specific expressions for our constants, but that is not so critical when we consider this general form for the solution. In case of the overdamped situation, we need to highlight this fact again here, that gamma is larger than omega naught. Since we subtract in this square root is gamma square minus omega naught square, we can also write that gamma will be larger than square root of gamma square minus omega naught square. Means that here we have minus gamma and here is minus gamma, which we just took out from the parentheses. And this minus gamma will be larger than square root next to it. So even if we add to minus gamma this square root, it will be still negative. The total exponent of this exponential function will be negative in both cases. So we will have just two terms which will exponentially decay over time. So we don't have any periodic component here, and means that if we start some like take out of equilibrium condition, such as system, block, string, and in the overdamped case, there will be no oscillations. This will just result in exponential decay over time from the excited state to equilibrium state, and that's all. So the fact that it's overdamped excludes any possibility in the periodic motion. So you see, we don't have any sinus or cosinus functions here. So it's just decaying exponential functions. So now let us go to more interesting case, which is a bit more complicated, but definitely more interesting. And that is underdamped case. So in this case, gamma will be smaller than omega naught. If gamma is smaller than omega naught, then square root, which goes into the discriminant of the characteristic equation, this gamma square minus omega naught square, will be negative. So our discriminant will be negative and means that our solution for characteristic equation, lambda 1, 2, how it was, minus gamma plus minus square root. It's equal minus gamma plus minus square root gamma square minus omega naught square will be exponential solution. So both our solutions will be exponential. Sorry, not exponential. There will be complex functions. And how we can write it in a proper form to highlight that these are complex. So we know that square root of gamma square minus omega naught square is smaller than 0. So it's square root of some negative quantity. So we can write that this is equal to square root of minus unity times omega naught square minus gamma square. And this minus unity, square root of minus unity, is I, imaginary unit. So we can write I times omega naught square minus gamma square. So this is our complex form of our solution, because we know that gamma is smaller than omega naught, and that's why this expressions actually will be correct to write just like this without square root. That gamma square minus omega naught square will be smaller than 0. So now our complex solutions for lambda 1 and 2 will be minus gamma. This part, this term is real. And then it will be plus minus I, imaginary component of our solutions, times square root omega naught square minus gamma square. Okay, so that will be the solution of our characteristic equation, assuming underdamped case when gamma is smaller than omega naught. So the general solution for our differential equation in this case will look like this. So it will be x as a function of t, will be e in the power of minus gamma t. So it's exponent which we took out from the parentheses before. And this is real part. And here we will have C1 prime, which is some complex quantity, constant, but it will be already complex quantity, not real, times e in the power of I times omega t, and plus C2 prime times exponent in the power of I minus I omega t. And here omega, we make a substitution that this omega is equal to square root of omega naught square minus gamma square. So we have this expression here in our solution for characteristic equation. In order not to write it every time the square root in general solution, we make substitution, put just some omega equal to this square root omega square minus gamma square. And this is the form. It looks the same as previous solution. We have term exponent minus gamma t out of parentheses, two constants, and some exponential functions. However, in this case, that is a complex function. And when we have a complex function, physical meaning possess only real component of this function. Imaginary component doesn't bring any physical meaning. So that we will keep in mind. And also we need to recall Euler's formula. There is a relationship between complex number in exponential form, as written here, and in trigonometrical form. So we can write that exponent in the power I omega t can be represented as cosinus omega t plus I times sinus omega t. So this is Euler's formula, and we will need to use it in our consideration. But it will be a little bit late. So now we need to go from complex quantities C1 prime and C2 prime, these constants, to express them in complex form, because now these are just some names of these constants, but we need to express them in complex form in order to have the whole terms which are in this equation in complex form. So let us write this down, the general solution on next slide. X as a function of time is equal to exponent minus gamma times t. Here is C1 prime exponent. Okay, we don't write exponent, we write now e in the power. Okay, e times I omega t plus C2 prime times e in the power minus I omega t. So this is our solution. Now C1 prime as a complex quantity, some complex constant, we can express in the complex format. So it's some constant C1, which is a real constant, times e in the power I times phi1. And constant 2 prime, the complex constant, is C2. C2 is already real constant, times some complex quantity I, e in the power of I phi2. So now we can write this part, which is complex function of our solution, because this one is real and this is complex. Let's call it x prime over t, and the total solution will be e in the power minus gamma t times x prime as a function of t. So we now are interested in this complex part of our solution, x prime t. So let us write it down in format when every quantity will be given in terms of real and imaginary components. So here will be x prime as a function of t will be equal to, instead of C1 prime, we put C1 times e in the power I times phi1. C1 times E I V1, then times E in the power of I omega t plus C2 prime, so we put this guy instead, C2 times E in the power of I phi2 times this exponent. So it will be E in the power minus I omega t. Okay, now we can group them together. It will be C1 in the times exponent in the power of phi1 plus omega t. Then plus C2 times exponent in the power phi2 minus omega t. So we have now, sorry, I forgot I and I here. These are complex functions. Okay, now we have everything in given in complex format. So we have a real constant C1 and C2 and two complex functions. Now it's time to apply this Euler's equation and split this exponential forms of complex functions into trigonometric format when we have real and imaginary components separate. So let us write again on the new slide this expression. So we have more space and can apply this Euler's equation, Euler's formula to this final expression. So we write it on the new slide. X prime as a function of time is equal, look again here, C1, P1 plus omega t. C1 times E in the power of I P1 plus omega t. And here will be plus C2 times E in the power minus, no, here we will not have minus, we will have minus in the parentheses, minus omega t. It will be also I times phi2 minus omega t. Okay, so now we apply Euler's formula. Let me write it down again so we have it in front of us. Exponent in the power of I times omega t will be equal to cosine omega t plus I times sinus omega t. So this will be real component and this is imaginary component. So now we split our terms. We have two terms, complex in exponential format, into real and imaginary components by applying this Euler's formula. So we can write that x prime as a function of t is equal. So first we have C1 times cosinus phi1 plus omega t. This is real part of this first term. Now we need its imaginary part. It will be plus I C1 times sinus phi1 plus omega t. So now we are done with the first term, and we need to write the second one. Will be C2 times cosinus P2 minus omega t plus I C2 times sinus P2 minus omega t. Okay, now we have done this task. We applied Euler's formula to our x prime as a function of t. And what we need to do next, we need to group real to real and imaginary to imaginary. So apples to apples, oranges to oranges. Then we have real part, and here is real part. Here we have imaginary part, and here we have also imaginary part. So that will be equal to C1 times cosinus P1 plus omega t plus C2 times cosinus P2 minus omega t, and plus, now we are done with real part. So imaginary part, we have I and open square bracket. It will be, first our imaginary component is C1 times sinus P1 plus omega t plus C2 times sinus P2 minus omega t. Okay, now we finally have everything grouped. So we have first real component and second imaginary component of our function x prime as a function of t. So as I mentioned before, we care only about real solution, which makes physical meaning. And we will get it only in that case when imaginary component of this function will be equal to 0. So let us try to figure out under which conditions our imaginary component will be equal to 0. So we can write down this imaginary component of our function separately and set it to 0. So let us do it on the next slide. So it will be C1 times sinus P1 plus omega t plus C2 times sinus P2 minus omega t equals to 0. So when it will happen, so we can write that C1 times sinus P1 plus omega t will be equal to minus C2 sinus P2 minus omega t. So now we can put this sinus in the, this minus in front of C2 in the argument of sinus, and we can change the sign of the argument of sinus. So in order to get rid of this minus in front of C2. So then we can write C1 times sinus P1 plus omega t is equal to C2 times sinus minus P2 plus omega t. And we see from here that this will be equal, left and right side, only when we have phi 1 equal to minus phi 2. Then left and right side of this equation will be equal to each other. And as a consequence, our imaginary component will be equal to 0. Means we will have a solution of our complex function, which will give us only a real component. And that what has physical meaning. And that's why what we need to do, we need to substitute. Now we need to come back to our real component. And instead of phi 2 here, we will substitute here minus phi 1, because we know when we have phi 1 and minus phi 1 in the second term, the imaginary part, we have already shown this, will be equal to 0. So that is the specific case when we will get a physically meaningful solution of our complex function x prime. So if we now, for this x prime as a function of t, for real, let's put it here, real part, we'll substitute a condition when phi 1 is equal to minus phi 2. So it will be C1 times cosinus phi 1 plus omega t plus one second. Yes, here will be another C2 times cosinus minus yeah, now it's clear why not C2. So again, here this left and right side will be equal to each other when phi 1 is equal to minus phi 2, and I forgot about this, and C1 is equal to C2. C1 is equal to C2. So we need to substitute in the real part of function x prime both C1 is equal to C2 and phi 1 is equal to minus phi 2. So I forgot about this part. So that's why we can write here C1 instead of C2, because they are equal to each other. And instead of phi 2, we write minus phi 1 minus omega t. So now we need to change the sign of the argument next to cosine, but that will not change the sign of cosine because it doesn't matter if it's plus or minus argument of cosine, it will give us the same result. So it will be equal to C1 times cosinus phi 1 plus omega t and plus C1 cosinus phi 1 plus omega t. So actually we have two identical terms here, and that will be equal to 2 times C1 times cosinus P1 plus omega t. So now we finally coming to the final expression. So that is x prime t. And we are interested in x as a function of t, and that was exponent minus gamma t times x prime t. And that is exponent minus gamma t times 2c1 times cosine phi 1 plus omega t. Now, if we apply some boundary conditions and define explicit values for constant C1 and Phi1, so we can substitute the 2C1 is equal to A amplitude value, and Phi1 is equal to phi some initial phase. And our final solution for damping under damped periodic oscillation will be x as a function of t equal to a times exponent minus gamma t times cosine phi plus omega t, where we remember that omega, we made the substitution earlier. That stands for omega is equal to square root of omega naught, the initial angular frequency, like intrinsic angular frequency of the spring block system, minus gamma squared. So eventually, what do we get? We had kind of interesting damping oscillation. If we have here time and here is x, so we have something like this. We have decaying amplitude from here and here. And this curve, which defines how the amplitude of the oscillation decays over time, is our prefactor. It's A times exponent minus gamma times t. And we still have periodic motion, but with time-dependent amplitude. But this frequency is already not omega naught frequency, which is equal to square root of k divided by m, if for the case when we don't have any damping. But the frequency of this decaying oscillation will be equal to square root omega naught square minus gamma square. So the higher damping will be, the larger deviation will be from the intrinsic oscillation. And then it will come to that point when we will go to overdamped oscillation, overdamped case, and there will be no oscillation. There will be just, as we discussed at the beginning, we have t, here is t, and here x. It will be some exponential decay without any periodic motion. But for under damped case, we observe still periodic motion, but exponentially decaying amplitude. So this discussion was quite heavy with equations, definitely what you have to remember, that is the final solution, and need to be able to explain that frequency of the under-damped oscillation is given by this equation, and amplitude of under-damped oscillation decreases over time according to the prefactor in front of this cosine. However, I believe that it would be good to go through the derivation, which usually not given in the textbooks for you guys, and to understand where it comes from. So the key message is to be able to first recall this equation for underdamped oscillation and explain each term, provide its physical meaning. Okay, thank you very much for your attention. Have any questions?
Well, you explained it clearly, so I guess I understood it. I got the point. Thank you.
Okay, yeah. Thank you for attention. Have a good evening. Sorry for postponing this lecture. I didn't have other choice, had to go to this business trip. So starting from Monday, we proceed further with normal schedule, and we use this recurring Zoom link as you used before for our lectures. Okay, take care and have a good evening.
Goodbye.
Goodbye.
Yeah, bye-bye.